Dynamics of the 11th class. So in this thermodynamics, the topics that we are going to see is the first law of thermodynamics and the different types of the thermodynamic processes. That is nothing but then your isothermal process, isobaric, isochoric, adiabatic, and the polytropic process, and heat engines, carnot engine, and the refrigerator. So these are the main concepts that the most number of the sums that are been appearing in this particular chapter, from which you can easily score some 8 to 12 marks. Okay, so now coming to our first law of thermodynamics. So before going for exactly the first law of thermodynamics, we would like to discuss some of the essential concepts. The first one is called as the thermal equilibrium. So what do you mean by this thermal equilibrium? So thermal equilibrium means where the system or is going to be maintained at the same temperature. In the sense, for example, there are certain two blocks are there, so or else two cubes or two containers are there, where the mass is going to be some m1 and the specific heat is going to be the s1. And now the temperature of this one is going to be somewhere around some 30 degrees centigrade of this one. Let us take like this, and this is connected to another container where the mass is going to be of this one m1 and the specific heats are good. This one it can be written as and some s2 where its temperature is somewhere around 70 degrees centigrade. Then if the heat will be transferred from the higher temperature to the lower temperature, in this direction the heat will be flowing, and finally the temperature is going to be attained at some 50 degrees centigrade, which is an it's called as thermal equilibrium. Thermal equilibrium. Okay, so this is the one of the things, please. So based upon this particular thing, your zeroth law of thermodynamics will be there. So that is nothing but an if two systems are in thermal equilibrium with each other. So for example, that is the zeroth law of thermodynamics. Law of thermodynamics. So if two systems are in thermal equilibrium with the third one, suppose in the sense A is in thermal equilibrium with the C and B is in thermal equilibrium with the C, then A and B are also in thermal equilibrium. Thermal equilibrium. Fine. So this is the condition. So coming to our first law of thermodynamics. So what is this first law of thermodynamics? It works on the conservation of uh, energy conditions. First law of thermodynamics. So it works on the conservation of, that is conservation of energy for a gaseous system. So for a gaseous system, that means whenever you are supplying some certain heat to any particular system, that will be used as an increase in the internal energy, and some work is being done by the system. That is, it consists of the three parts. One is going to be the heat supply, to a system. Second one, so what does it does? It's going to be increase in internal energy, increase in internal energy of system. And the third one is going to be the third part. Some work is being done. Work is done by the system. Work is done by the system. Okay. So now, suppose sort of a system is there like this. There is a system like this, and you are supplying an amount of the heat to it. That is the dq you are supplying, and on that one, your internal energy is going to be the rising case here. That is du, and the work is done by the system. That is dw. Okay, so these are the basic things, please. So the first law of thermodynamics can be written as and that is dq is equal to du plus dw. So this is the differential form of the first law of thermodynamics. Differential form of first law of thermodynamics. So this you can take it as an FTL, first law of the thermodynamics. So what are the parameters of the thermodynamic parameters in this case? That is an heat supply, change in the heat supplied is the one, change in the internal energy, and this is your work done conditions, please. So these are the parameters in this particular gaseous process for the first law of thermodynamics conditions. Okay. Now, so whenever we supply the heat to the system, when the heat is being supplied to the gaseous state, that is, the heat can be in the process of that is dq is equal to, it can be equal to the n into specific heat, or that is mass into specific heat, ms delta t, it can be the case. That is a change in temperature, or from this C is called as or S is called as a specific heat of the substances. If it is concerned to the gas, then it can be written as dq is equal to or nc into delta T, change in temperature. Okay, so this is for the gaseous conditions. This is for the solids and the liquids cases, please. From this one, you can identify or you can find the q is equal to integral of n c into dt, where the temperatures might be changing from some T1 to the T2. This is then this way you can find out the heat supplied cases, please. So now the next part of this case, that is nothing but an change in the internal energy. So next important part is that is a change in internal energy. So what is this change in internal energy? As we know, according to the equipartition or your energy U is equal to, it can be the F by 2, that is the degrees of freedom F by 2 into N into RT. So from this one, you can say that internal energy is directly proportional to the absolute temperature. So that means if the temperature of the gas is increased, then the internal energy will also be increased. So from that one, you can say that du can be written as that is change in internal energy is can be F by 2 into Nr into dt, where the temperature might be changing from the T1 to the T2. So this is the one where the temperature will be changing here from T1 to T2 conditions. So the internal energy, or if you want to find that is U is equal to anything, or integral of the du can be obtained as an integral of this is F by 2 into Nr into dt, where the temperature is changing from the T1 to T2. Or it can also be written as an U final minus U initial conditions for solving certain sums. So for all kinds of the processes, whatever may be the processes, you can write as delta U is equal to F by 2, that is degrees of freedom, into NR of this is T2 minus T1. So this is a change in the internal energy. And the important part of this one is going to be the work done. So work done in this particular process can be written as an suppose if you take any particular container to which you are supplying some heat to in this one, and let this be some massless piston where the inside some gas is being filled here. So because of whatever the heat that is supplying, if the piston is going to move certain distance of an uniform cross-sectional area, if the piston is moving some distance called as an dx, and it is having an uniform cross-sectional area of the A, and there is an increase in this particular dx value in this case, then work done can be written as an dw is equal to, so P into change in the volume, or the surface area is been changing into dx, or this can be written as an P into dv. And if you want to calculate the total work done, W will be an integral of, this is dW is equal to integral of the pressure P dV. V is the pressure and volume, this is V1 to V2. So these are the very important things in this case. Now if we go for the work done conditions, so if the gas expands, if gas expands, then work done you can say it as a positive. And in this case, if gas compresses, then work done is negative. So these are the major important things we need to remember. Or graphically, if you want to find the work done is can be taken clockwise sense, it will be taken as a positive, and anti-clockwise sense, you can take it as a negative conditions for the first law of the thermodynamics. So depend upon the work done by the system, it will be taken as a positive, and work done on the system, it will be taken as a negative. So the most of the sums or the most of the practicing will be done on the this first law of the thermodynamic conditions, please. So now, what are these specific heats? As we have mentioned in this particular case, the specific heats of this one, that is the molar specific heats. So what is this molar specific heat? Is be nothing but a C. So the units of the C can be written as a joule per, this is mole Kelvin. So specific heat is nothing but an amount of the heat required to rise the temperature by 1 degree centigrade by supplying an unit amount of this one or unit mole of the gas. So two types of the specific heats will be there. One is an molar specific heat. Molar specific heat at constant volume, represented by Cv, and second one is going to be the molar specific heat at constant pressure, which is being represented by the Cp. Okay, so anything, any definition, the Cp or Cv definition wise, both of them will be the same conditions. The heat required to rise the temperature by 1 degree centigrade at the constant volume, and for the constant pressure, heat required to rise the temperature by 1 degree at constant pressure conditions. So that is dq is equal to, if, so for example, if in the case it's a using of this particular first law of thermodynamics, or you can say this one as an from the first law of the thermodynamics or anything like that. So from the first law of thermodynamics, from first law of thermodynamics, you can use it. Suppose if work done dw is equal to 0, then what will happen, sir? Here dq is equal to du. So dq is equal to du in the sense, if I take this as an, that is a du value we know, heat supplied is, that is ncv dt, if I write it like this, and du from here, if I can replace du value, that is f by 2 into nr into dt, then it can be written as and simply, that is cv can be is equal to the F by 2 into R. For a monoatomic gas, it's going to be the uh, for the monoatomic gas, your degrees of freedom F is equal to 3, whereas it's a diatomic, F can be replaced as an 5. Then the CV values can be written as an, for the monoatomic CV is equal to, it is 3R by 2, and for the diatomic it is CV is equal to 5R by 2, but don't take it as a granted. The specific heat is going to be dependent upon the temperature conditions, please. So now, before directly going for the specific different processes, just I'd like to continue this one, the specific heat of this one. So the relationship between the CP and the CV can be written as, then it is CP minus CV is equal to R. This is one of our relation between the specific heats of the gases, and the gamma is equal to, it is Cp by Cv, where it is the ratio of the specific heats uh, for the or different kinds of the processes, that is monoatomic or the diatomic gases. Cp and Cv values, you can find it out correspondingly. That is, Cp value will be the 5 R by 2 for the monoatomic, and the Cp is going to be the 7R by 2 for the diatomic gases. So, or from this one, you can also write for the degrees of freedom and relation between the degrees of freedom and the gamma value can be written as, and that is F is equal to degrees of freedom, it is 2 by gamma minus 1. From this one, you can use the relation CV is equal to R by gamma minus 1, and CP is equal to gamma R by gamma minus 1. So these are the very, very important relations in this particular scenario situations, please. And from this one, you can write further, internal energy can be written as an internal energy U is equal to, it can be written as an F by 2 into, this is nRT, or you can use it as an, this is N CV into T, or if I replace that CV value here, that will be the nRT by, this will be the gamma minus 1, where nRT can be ideal gas, it can also be written as an PV by gamma minus 1. So these are your very, very important relations concerned to this one. So please be careful of this one. So you need to remember all these information and all these things, please. So now coming to the different types of the processes in this case. So majorly we'll be discussing with an different types of the processes. First one is an choric process. So what is this isochoric process? It is a process in which where the volume of the volume remains constant. So since the volume remains constant in this particular case, what we can define here, sir? Well, since the volume is going to be constant, that is work done can be equal to that. That is, you can say that dW is equal to, as we have written, dW is equal to PdV, change in the volume. Since volume is equal to constant, work done can be written as an 0 in this particular cases. So since the work done is equal to 0, then what can happen in this case? dq, whatever the heat supplied, that will be only utilized to rise the internal energy. So since it has been rise to only the internal energy conditions, fine. So now next process, if I go, since the work done is equal to 0 in this particular case, du dq is equal to du conditions, which can be written as an ncv into dt case, please. So now in the second process, where it is called as an isobaric process. So what is this isobaric process where the pressure is going to be, pressure is constant, and we can use the from first law of thermodynamics. That means dq can be written as an it is du plus dw, that is work done in this case. So dq can be written as in that is dq is equal to at constant pressure cp into dt, and this can be written as an ncp of this is T2 minus T1. Temperature is been changing here. This is your heat supplied conditions. If I want, you can also replace the Cp value. This is N into gamma R by gamma minus 1 of it is T2 minus T1. And simultaneously, that is du can be written as an it is ncp into dt, or this is ncp, so cv of ncv dt, ncv of this can be written as an t2 minus t1. And the work done in this process, W is equal to, or dW is equal to P dV, where the volume will be changing from the V1 to V2, if you know specifically, or else integral of work done, or dW, can be written as a P into integral of the dV, where volume is changing from the V1 to the V2. Or this can be implemented as P into this is V2 minus V1. This is your work done under this particular isobaric process. So next important process, I would like to go for this one as an isothermal process. So in this case, that is your third process, which is an isothermal process. So what is this isothermal process? In this one, temperature T is equal to constant. Since the temperature T is equal to constant, change in the internal energy will be zero. Internal energy is not zero, sir. Change in internal energy is equal to zero. That means whatever the total heat that you are supplying will be, change in the heat will be equal to the change in the work done. Okay, and work done can be calculated, or the Q is equal to, or the work done heat supplied, or the work done is equal to the integral of P dV, where the volume is changing from the V1 to V2. On solving and replacing the P with nRT by V, and use solving this one, you will be getting the work done as an this is nRT into ln of V2 by V1. Or since it's an isothermal process, Boyle's law will be valid over here. So that means according to the P1 V1 is equal to P2 V2 relationship, we can also replace the V2 by V1 as P1 by P2. This also can be used, and this is the work done under this particular process. Work done is equal to nRT into ln of V2 by V1. So this is your isothermal process, most important process. So in this case, in the isothermal process, if we go for the graphical thing, so that means if we analyze the graph drawn between the work done is nothing but an area under the graph of the pressure versus volume. The shape of the graph is going to be the inversely proportional. The area under this particular graph will give you the corresponding work done. Suppose this is the volume V1 at a pressure called as this is the P1, and this is the volume V2 at this pressure called as an P2. Things, please. So this entire area, whatever is the area under the curve, will give you the work done. Area under the curve is equal to work. Fine, sir. So now as the change in the temperature is equal to 0 and everything, delta T will also be equal to 0. And these are called as an isotherms where the different values of the temperatures, if you can draw this one, pressure versus volume, for the different values of the temperatures here, the area under the curve will be gradually increasing. Let this be the temperature T1 and this is your temperature T2 and this is your temperature T3 where T3 greater than T2 this will be T1. So as the temperature gradually increases, your area under this will also increases and these are called as an isotherms. Fine. So this is regarding the isothermal process. So since under the isothermal process, your temperature is constant. So then what can be the specific heat under this particular case? So delta T is equal to 0, that is specific heat C is equal to 1 by N into this is dQ by dt. Since the dt is equal to 0, then the specific heat under the isothermal process C is going to be will be infinity. Okay, so this is the one of the important things, sir. Next one, next type of the process I would like to deal with is an adiabatic process. So that is an adiabatic process. So what is this adiabatic process? Where in this case that is dq will be equal to 0. Change in the heat or the exchange of the heat from the surroundings or to the system or from system to the surroundings, that's not going to happen. So since dq is equal to 0, so from first law of thermodynamics you can say that d uh, w or du is equal to minus of dw. So that is a change in the internal energy is negative of the work done. So that means if the work done on the gas is there, for work done on the gas, then the internal energy will be increased, and work done by the gas, then the internal energy is going to be the decreasing conditions. So since heat supplied is equal to 0, the change in internal energy you can write it as du is equal to ncv into this is T2 minus T1 where Cv is nothing but an you can write it as an n into this is R by gamma minus 1 into this is T2 minus T1. This is your internal energy. And as we know that work done is equal to minus of du, if you can write it, then the same equation can be written as an nr by gamma minus 1 of it is T1 minus T2. So this is your work done conditions. In a different situations where it is not available, if you take the NR into the sun, if temperatures are not available, then it can also be written as an P1 V1 minus P2 V2 by this is gamma minus 1, where gamma is called as a ratio of the specific heats. So in this case, the relationship between the pressure, volume, and the temperatures will be changing. So relation between the thermodynamical physical quantities, pressure, volume, and temperature if you want to deal with this one. So how does the relations are going? So since here the temperature is not constant, the thing is temperature is not constant. So pressure is going to be no more directly proportional to inversely proportional to the volume. So we need to establish a new relationship again between the pressure and the volume. So according to that particular relationship, or when you derive that particular relationship, you can say that PV to the power of gamma is equal to constant. So this is the relation between the pressure and the volume in the adiabatic process. And coming to the temperature, T V to the power of gamma minus 1 is equal to constant. And another relation between the temperature and the pressure. So T to the power of gamma and P to the power of 1 minus gamma is equal to constant. And the slope of the graph, the slope of under the adiabatic process, if you plot a graph, the slope of the graph is going to be more than the isothermal process. So since PV to the power of gamma is equal to constant. Now if I differentiate this equation, so on differentiating this one, you can write it as an, this is P into gamma V to the power of gamma minus 1 into dV plus V to the power of gamma into dP is equal to 0. So now taking them to the other side, this one please, that is V to the power of gamma into dP is equal to minus of P into gamma into V to the power of gamma minus 1 into dV. Now I'm trying to get the slope here, please. That is dV by dV is nothing but a slope of this one is equal to negative of P into gamma into V to the power of gamma minus 1 by V to the power of gamma. So this is equal to the dP by dV is equal to, this is gamma terms of minus of, this is PV. So this extra term gamma is been available. So due to that reason, the steepness of the adiabatic process or the graph steep between the pressure and the volume curve will be more than the isothermal curve like this. So let this be the volume V2 and here let this be the volume V1 at the corresponding pressure values of this one. The pressure at this point is going to be the P1 and the pressure at this particular point is going to be your P2. So as P is inversely proportional to it's a rectangular hyperbola V to the power of gamma. So these are your different relationships, please. Now, when you observe the slopes under these different processes, so just keep it aside. When we observe the slopes of under this particular process, so that is steepness of, if I want to tell you that is slope of this one, that is dP by dV under adiabatic process is equal to gamma times of slope of that is dP by dV under modulus of this is isothermal. So this is the one and always gamma will be greater than 1 sir. This is the one another important condition that we need to remember this. Okay, so different processes, that means different types of the gases is monoatomic, diatomic. You will have the different values of the gammas, where the different values of the gammas are nothing but Cp by Cvs of that particular gas, monoatomic or your diatomic condition. Now coming down to this particular concept, that is heat engines, Carnot engine, and then another one is going to be the refrigerator conditions. So coming to the heat engines and Carnot engines. So heat engine is a process where in which what is going to happen, sir? There will be majorly three different parts where will be there in the heat engine conditions. So what are that major three different parts? So heat engine consists of and one is called as a source. So let this be the source which is going to supply the heat, which will be at the higher temperature T1. So from this one, the heat is being supplied to the system. So how much heat is being supplied? Let it be the Q1 is the heat is being supplied to a system. And here there will be the work is being done, or you can call it as an engine where the work is being done here. And whatever the amount of the heat that is being left over or the rejected amount of the heat will be turned out to the sink where the temperature is going to be the lower temperature, that is T2. In this case T1 will be greater than the T2. This is your heat engine condition. So But according to the total heat supplied, whatever you're doing, the total heat supplied here is being utilized. Q1 is being work done plus that is Q2. It is nothing but according to the law of conservation of the energy. From this one, you can say that work done is equal to Q1 minus Q2. Then. So this is your thing, and the efficiency of the heat engine can be written as an eta is equal to work done by Q1, that is nothing but an work done by heat supply. So you need to only consider what is the amount of the heat supplied only. So that is the thing you need to take into consideration. Please be careful in applying the here relations for the heat engines. So that means the eta can be written as an eta is called as an coefficient of efficiency of the heat engines. So the efficiency of heat engine is equal to that is work done by heat supplied, that is Q1. Work done can be written as an it is Q1 minus Q2 by it is Q1 conditions, please. So or this can also be written as and this is 1 minus this is Q2 by Q1, which is equal to the 1 minus that is T2 by T1. So these are our basic relations regarding the heat engine conditions. Next, when I'll just try to go for the refrigerator here, the refrigerator or the AC is what's going to happen here. It's a reverse of the uh, heat engine conditions. So what's going to be happening in this one? The working substance, whatever is there, the working substance is going to be take the heat from the sink. It's going to take the heat from the sink. Okay, so and to divert it towards the source, which is at the higher temperature T1. This is at the lower temperature T2. So heat is that is Q1 is going to be there and taken out. This is going to be the Q2 and remaining thing whatever is going to be the work is done by the system here. That is work done is W. So from this one here, Q1 plus work done W is equal to Q2. So if this equation you can write it from the same thing, that is conservation of the energy conditions. So now coefficient of performance you will be calling it as in beta. In some cases it will be written as in beta or some other case it's called as a coefficient of performance. So which is equal to the Q1 by W or which is equal to the modulus of Q1 by mod of it is Q1 minus Q2. So this is called as your coefficient of performance for the refrigerators. So this is another very important thing, sir. So coming to the last part of this one, which is the another type of this one, is called as a carnot engine. Like technically speaking, or the practically no engine is a perfect engine. So, no, but this Carnot cycle is a theoretical one where it is trying to show that the 100% efficiency of this one, that is heat supplied is totally utilized as the work done and remaining heat is being gone to the sink. That is, it's perfectly satisfying the law of conservation of the energy theoretically. Practically, it is been difficult to undergo this particular, that is, whatever the heat supplied is being completely utilized to the work done without any particular loss. So, if you observe this Carnot cycle, or in this case, it will be undergoing the different processes, that is, the pressure versus volume. The first step of the process, suppose it is starting from the A, where the thermodynamical physical quantities are, let them are going to be the P1, V1, and the T1 at the A, and it is being undergoing the process of isothermal expansion. Isothermal expansion. So let it be the B at this particular point where the temperature T1 is equal to constant, and from the B it is been where the heat remains constant and the temperature is been changing. It's an adiabatic expansion here, please. Another one from C to D, it is undergoing the isothermal compression, and D to A, it is adiabatic compression condition. So let me write this one. This is from A to B. It is isothermal expansion. So since it's an isothermal expansion, the work done or the heat supplied Q is equal to temperature remains constant. So work done under this process A to B can be written as an nRT1 into ln of volume is been changing from, suppose, V1 to V2, that is V2 by V1, it will be coming under this one. So it's a work done under isothermal process. Now B to C is an adiabatic expansion. Adiabatic expansion. So adiabatic and the adiabatic expansion, that is your Q or the dq value is equal to 0. So work done under adiabatic condition, that is B to C, is equal to the NR by, this is going to be the gamma minus 1. Temperature is changing from the B to C, that means T1 minus T2. Let the temperature at the C is going to be the T2, and the temperature here it will be remaining as a T1. So this is the work done in this particular case. So in the BC, we are not supplying any heat, only in the AB part, we are supplying the heat. Now coming to the rest part of this one, that is from CD. In this CD, in this process, what is happening? It is an isothermal compression. Isothermal compression. Since it's an isothermal compression case, dq again the same thing, that is work done under C to D, it will be a negative case. Basically that's going to be the NR. T2 temperature is been constant at the C and D, it remains as in T2. NR T2 into ln of, this will be the volume, and it has been again changing from the, suppose the volume at the B is going to be the V2 and this one is going to be the V3, and it is changing to the V4. So that means I have to write it as a V4 by V3 with a negative sign, because its volume is been decreasing. In this case, at the A, let the volume is going to be the V1. Fine. So these are the things. The heat is being. This is the heat taken out from the system. You are extracting the heat here from. Since it's a negative thing, you are extracting the heat from here. It is not the heat supplied case, please. So and last process where D2A is called as an adiabatic compression. So what is this adiabatic compression? Where again the dq heat will be, change in the heat will be 0. It's not been exchanged to the surroundings, or heat is not taken from the surroundings. So work done under this process is going to be the, that is W of the D2A is also the negative thing, that is NR by gamma minus 1 of, what can be this particular thing, sir? NR by gamma minus 1 of, this can be written as a T temperature of the D minus, that is T2 minus, it is T1. So this is the one thing, please. So next case. So when you see for this one, since it's a cyclic process, the total internal energy du is going to be coming down. Total internal energy is equal to 0. And due to this one, the total heat supplied, that is the Q, total heat from the A to B plus heat, in this case, that is B to C, is anyway 0. And this is going to be the C to D, this is a negative. This is the 0 value, and this is going to be the heat in this process. B to C, this is the D to A. This also zeros. These two things are going to be zeros is equal to the work done between the A to B plus work done between the B to C plus work done between the C to D, work done under the D to A. So these two works will be equal to the Z, these can be removed here. Okay, so on solving this one, our finding for the efficiency of this one is equal to the total work done by heat supplied only. So if this can be the efficiency of this can be written as an this is simply 1 minus T2 by T1, or as I have written earlier, this is T1 minus it is T2 by T1. So this is the efficiency formula where T1 is nothing but, and when you want to relate it to the heat engine, this is your source temperature, and T2 is called as an sink temperature. Fine, sir. So this is regarding the Carnot cycle. So most of the questions, or a lot of questions are being asked on this particular thing. So hope you just got the information sufficiently. Work hard, please.